Okay, I'm going to go through an example problem here for relative velocity, and to do so I'm going to do number 39 here from your homework. So if we look at this, it says a boat can travel at 2.3 meters per second in still water. If the boat points its prow, which is the front of the boat, directly across stream whose current is 1.2 meters per second, what is the velocity of the boat relative to the shore, and what will be the position of the boat relative to its point of origin at 3 seconds? Okay, so first thing I'm going to do is I'm going to make a drawing. Okay, so here's the shore, here's the boat. Okay, and it's going to, in the problem it says the boat can travel at 2.3 meters per second in still water. So if it's pointing directly across, like this line can represent the velocity of the boat relative to the water, and it's 2.3 meters per second. Okay, and then it says that there's a velocity of the stream, of the current, that is downstream. I'm just going to consider right to be downstream. And this has a velocity of the water relative to the shore that is 1.2 meters per second. Now, what you'll notice here is that we've just made a right triangle. Okay, so if I want to solve for the velocity of the boat relative to the shore, well, the boat's going to move off in this direction. So this would represent the velocity of the boat relative to the shore. That's what we're looking for. Okay, so you'll notice this is the hypotenuse, the opposite, and the adjacent side of a right triangle. Okay, so that means we can use Pythagorean theorem, c squared is a squared plus b squared. Or we can use the more physics version, where the vector quantity that we're looking for squared, it would be equal to the vector quantity's x component squared plus the vector quantity's y component squared. Alright, so if we're actually solving for that particular vector length, this VBS, that would be this. Okay, so that would be equal to the square root, to get rid of that squared value right there. And then I'll put the x value, which was 1.2 squared. And then the y value, 2.3 squared. Just like that. Okay, and if we do that, you should get a velocity of the boat relative to the shore to be 2.59 meters per second. Okay, now this is a vector quantity, therefore this has to be at a particular angle. And since the question asks velocity of the boat relative to the shore, then it would make the most sense to actually give this angle or this angle, and those are complementary, right? Or what is that? That's not right. Can't think of the name of it. Somebody can tell me later. But as long as we have a box, then this angle and that angle are the same, and this angle and that angle are the same. In this case, we could solve for this angle knowing that we have this and this. Okay, so to do that, this would be the opposite and the adjacent, yes? Alternate interior angles, I think, is that right? I can't remember. Okay, so let's do the inverse tangent and opposite and adjacent. So 2.3 over 1.2. Okay, and if we do that, I do believe you end up with 62.4 degrees. So once I actually have this angle, now I can write this as 2.56 meters per second at 62.4 degrees. And we already know that it's the velocity of the boat relative to the shore, so this is the velocity relative to the shore at that particular angle. Okay. Now that was part A of the problem. The second part of the problem, if we take a look, says what will be the position of the boat relative to the origin after 3 seconds? So we could think about this logically here. Okay, if it's traveling at 2.3 meters per second across, then the position across the stream is simply going to be, in this case, a delta x would be its velocity of the boat with the water times 3 seconds. Or, since this is 2.3 meters per second, then we could say that it will be 6.9 meters across the river. And if we wanted to say how far downstream it was going to be, then again, delta x, in this case it would be the velocity of the water relative to the shore times 3 seconds, and that there would have been 1.2. We can say that it is 3.6 meters downstream. Okay. So that's where it would be position-wise in reference to where it started. Okay. Now, this was a fairly easy problem. They get much harder. Have fun with number 46. I will give you a hint on both 46 and 49. The use of the law of sines might be helpful. If you don't remember the law of sines, sine of A over A equals sine of B over B equals sine of C over C. Okay, and that works for any triangle where, okay, if we know these, let's say this is A, B, and C, then this side is A, this side is B, and this side is C. They're always the opposite sides. Okay, and that works for things that aren't a right triangle. So that might be helpful. Okay, so hopefully this example gets you on your way, and good luck with the rest. All right.